Howdy everyone, I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I record all my lectures and put them online. This will be a lecture about frequentist probability. We'll take on the frequentist perspective proudly and show how we can count our way to probability. I want to acknowledge the fact that some years ago I was supported and helped as I just joined UT by Doctors Hardari and Lake, who provided some previous course content used in this course, and some of these slides probably greatly modified, but a few of them are still retain some of that essence and ideas from them. I want to recognize them for their just wonderful kindness to me and helping me get started with my courses and providing some content. All right, so let's talk about frequentist probability. What is it? How do we define frequentist probability? It's a measure of likelihood that an event will occur. Now, if we have a random experiment in well-defined settings, such as a coin toss, we have good control of the experiment. We can go ahead and define event A. And A will be a certain outcome. If it was a coin toss, it would be heads occurring with the coin toss. Okay, you flip the coin, you get heads, and you say that that was event A. We can define any event as being A. The probability of A occurring, which we'll use shorthand notation of PA, is going to be equal to the ratio of the number of times that A occurred over the total number of trials or experiments. And what we'll say is that N must be large enough. Now, we'll get more accurate the more experiments we run, but we'll talk later about the false belief in the law of small numbers and how dangerous it is to use too small of an experiment. But it has to be a large enough number of trials. So what would be an example of this? Well, what's the probability of a dry hole for the next well, or having sandstone occur in a reservoir unit, or exceeding rock porosity of maybe 15%, or anything it could be. So we define A, we run experiments. They should be careful experiments. We'll get more into issues around stationarity and so forth when we get more geospatial. All right, so the frequentist probability is all about experiments and counting. Get the ratio, that's your probability. Good to go, pretty simple stuff. Now we're going to use Venn diagrams a lot to define probability logic based on this frequentist approach, and we'll build up from it. We'll get all the way to conditional probabilities and Bayesian approaches for the next lecture. And so if we're going to talk about Venn diagrams, let's just make sure everybody's on the same page. This is a Venn diagram right here. It is a great tool to communicate probability. And so what are some of the things that we can observe directly from a Venn diagram? First of all, we're going to have samples that drive this, and there'll be an experiment and samples from the experiment, individual outcomes. Then from those outcomes, we will define different events, A and B. Those are two events. Now, if we have a certain outcome, then we'll define that from that sample as being event A occurring or event B, and they could jointly occur together or not. Okay, so then what we're going to do is we're going to have omega space. Now, this is the box. Now, if you're one of my students in my class and you're about to take one of my midterms, please draw the box, okay? Because the box is all possible outcomes. Omega, just as we mentioned in the previous lecture. And the problem is, if you don't draw the box, I can't really understand the Venn diagram, right? Because this is all possible outcomes. Now, the ratio of the area of B to the size of the box is, in fact, the probability of B occurring, right? So in this case, what would you estimate? Maybe about 20%, maybe 25% probability of B occurring, and maybe more like 10% or so probability of A occurring, and I'm estimating based on the size of the box. Now we could get out a tool and measure the areas, planimeter or whatever, and kind of figure that out, but we'll just eyeball it from here. Okay, so got to draw the box. If the box was way out here, then you could see the probability of A and B would be much smaller, and if the box was wrapped right around this tight, probability of A and B is much larger. Okay, now it's an excellent tool to visualize marginal joint conditional probabilities. We're going to get into that in this lecture, so I won't define that now. So let's get a really simple example. So we determined facies in a set of well cores, and we sampled at, say, 1 foot intervals along the wells. We've got 3,000 data. Our omega would be the 3,000 measurements from core. Okay, so far so good. Then we can go ahead and define event A and B. And so maybe our event A and B could be A is sandstone and B is some type of shale or something like that. So we define our events. And so instead of using A and B, I'll just call it shale and sandstone. Now we can go ahead and take the result from the 3,000 data and we can draw our Venn diagram. And this is pretty cool because we have all possible outcomes, the box, omega. We have the probability here of sandstone would be this area right here. The probability of shale would be this area here, and the overlap between the two would be a combination, which we could define based on lithofaces as being some type of interbedded sand shale type of lithofaces. And everything outside of this union of sand and shale would be other facies. Something else happened. Maybe there's carbonaceous type rock, wacky stone, bound stone or something. There might be something else going on in the system. Okay, so that's a basic example of a Venn diagram. I hope this makes it clear for you. Now let's go through a variety of different probability operators. And these are the basic building blocks to probability logic. And so the first one is the operator union of events. Now, this is pretty straightforward. We represent the union of events by this U symbol, so it's easy to remember. And it is technically for the set of all possible outcomes, X, that it would be the combination or the OR operator. So what are the set that include X within A or X within B? Now visually, this is why we like Venn diagrams. It's really easy to understand because the union operator is like if you were drawing a Venn diagram, it's the weld operator. It's basically taking these two shapes and welding them together. And this is what I'm trying to calculate. A or B would include the intersection of A and B. Also, it includes just B and just A. So it's this weld. And so this is the probability I'm trying to work out. Now, the intersection operator is different. The union operator was the OR operator. The intersection operator is the AND operator. Both must occur together, A and B. Okay, now the way I remember it is the symbol for the intersection is this upside down U. And to me, it looks kind of like an N. So I think of N intersection. It's kind of a way I remember it. So that's the AND operator. We'll introduce it more formally later as a joint probability. We'll get into that later, and we'll use different notation at that point too. All right, so unions and intersections. Now let's talk about complementary events. Okay, so the complement. And so if I have A event right here, I could also have the not A event. A did not occur, and we will call that the A complement. A superscript C for complement. All outcomes that are not A. Now, we can also have mutually exclusive events. This is pretty obvious. Events that don't intersect, they don't have common outcomes. The intersection of A and B, the AND operator, is a null set. It's an empty set. They never occur together. And in the Venn diagram, we would see it like this. They don't overlap. There's no purple area between them. All right, so basic probability. Now we can go all the way to exhaustive, mutually exclusive events. And so this is a sequence of events whose union is equal to the overall sample space. So the union of A1, A2, up to AN different events is going to be equal to omega. And I should also state that there's no intersection between them. So any pairwise intersection A1 and A2 is null set. Now, if we have exhaustive mutually exclusive sequence of events, the Venn diagram would look like this. Now, if you look really carefully, it's either red or blue. There's no purple. There's no overlap. There's no gap between A and B. There's no not A and not a B. It's all going to be either A or B. Okay, so that's exhaustive mutually exclusive events. we're going to use that to solve some interesting problems later on. So now the Venn diagrams that I've shown so far have been pretty simple. Probability of A is equal to the area of A divided by the area of omega. But of course, it could get really much more complicated. We can have all kinds of interesting intersections and unions, and we can work with many different events at the same time. Let me give you a very simple example here, but getting a little bit more complicated. The probability of drilling a dry hole in the next well, that could be a complement because A was drilling a well that was not dry, a producing well. Encountering sandstone at that location in space, if you got good rock at that location, that's B. Exceeding some type of critical threshold for porosity to have good amount of volume in place, that would be event C. And so we might be interested in the combination of a dry hole having sandstone and also having good rock porosity. In other words, this could be like a seal failure where you actually good reservoir rock, but there's no fluids in place that we want to recover. And so we could go ahead and look at the Venn diagram of the combination of all of these events, and now we're interested in this right here. Now, of course, this intersection right here would be the good rock. No seal failure at all. All right, so our Venn diagrams can get much more complicated. Now, a good thing to do is to give a little more thought to what an event is, how do we define event, and how do we relate that back to the original sample set. And this is somewhat trivial, but it gets our minds in the right place about it. Now, I want to acknowledge I show small sets here because of it would just be tedious if I showed you many samples. But in the back of our minds, remember, n goes to infinity, that part. If we're going to do any probabilities, we really need enough samples. And I've only shown you a case right here of 7 samples. So just keep that in mind. That's just for demonstration. Okay, so petrophysicist has measured porosity from 7 core samples from a carbonate formation, and they have these values right here. They've been sorted conveniently in order, and we want to define 3 different events. Porosity less than 15%. So that's a low porosity rock, and that's A, and you'll see A goes from here to here, the first 3 samples. Porosity greater than 20%, that's the really good stuff. That might actually be, if the permeability is also high, might be a thief zone, might be an area where we just have really high production, and something we should be aware of. And C would be this intermediate, and it's got a little overlap with A, and it goes up to right here, 17%. Okay, so we have defined 3 different events, and we could go through and work out the unions, the complements, the intersections of these different events, just to make sure we test our knowledge. So I'll invite you to pause the video right now and work through this on your own. I'm going to go ahead in 3, 2, 1 and show you the answers. So really straightforward right here. We have, in the case of the union of A and B, it'll just be the A events, 10%, 12%, 14%, and we're welding on, we're adding in the 25%, and that's it right there. So the intersection between B and C, well, B and C don't overlap. That's why it's nice to draw these boxes and look at it like this, so it's a null set. And the union of all of them will be all of the values excluding the one that was not in any of the sets. So I hope that's useful. Now to calculate the probabilities, well, we're going to assume it's enough samples, and we can go ahead and just use the frequentist approach, which is counting and ratios. We already counted, now we do the ratios. And so you can confirm this, there were 7 samples. And so now we're talking about the union of A or B is going to be just 4 divided by 7. The first 3 here from the set A, and this one adding to 4. And so we get that as a probability and so forth. If we take the union of all of them, now this is interesting. I just realized I have a little error here, so I apologize for that. The union of A, B, and C actually missed one of the values. So in fact, I should have removed it, and it should be 6 out of 7. So I was just testing you. Okay, anyway, I'll get that corrected. It's not bad. It just shows we're all human. So let's go ahead. We've just demonstrated this idea of intersections, unions, complements, and this idea of calculating frequentist probabilities from a simple sample set. Let's go through a couple more probability concepts. Non-negativity normalization. These are fundamental probability constraints, and they build on the basic axioms that we talked about in the previous lecture from Kolmogorov. And so what do we have here? First of all, probability must be bounded between 0 and 1. We understand there should not be negative probability. That would clearly end the universe. It would be paradoxical. That doesn't make sense at all. But it also makes sense that probability of an event can't be greater than 1. Super probability. It doesn't make any sense, right? 100% means it's going to happen. Are we paranoid? It's really should not go higher than 1. Closure, that all possible outcomes, if you take all of them, that's a probability of 1. Nothing else can happen. Now, we're not talking black swans or, unanticipated type of outcomes, but if we assume we know all possibilities, then for one of them to happen, probability of 1. And null sets, probability of something that never happens is going to be 0. Now, complementary events, if you have complementary events A and not A, now we know they're going to be mutually exclusive and they're going to be exhaustive because all possible outcomes are A or not A. There's no other option. And so we have closure. And closure means that if we take those probabilities and sum them together, it's equal to 1. As we can see here in the Venn diagram, A, and not A actually does cover the entire area, or all possible outcomes omega. All right, so let's talk about another probability operator. Let's talk about the addition rule. And this is a common mistake people make, is they forget to subtract the intersection. So this is how the rule goes. The probability of A or B, the union operator, is equal to the probability of A plus the probability of B, and then we have to subtract the intersection of A and B, the intersection, right? And so what are we doing here? We take the probability of A plus the probability of B. Now look what happened. We just double counted the intersected area, so we got to subtract it once. Now in the case we have mutually exclusive events, we could generalize even further. This would be any number of possible AIs, events, AI 1, 2, 3, 4, up to any number. What we can say is that the intersection between AI, AJ, where I is not equal to J, is going to be a null set. They're mutually exclusive. They never overlap each other. In that case, we use Kolmogorov's third axiom, which was in the previous lecture. And this, you'll remember, it's exactly what this is, in which we can just simply sum the probabilities because they're mutually exclusive to each other. There's no intersections, no double counting to account for. Now, given what we've just talked about, we could go ahead and solve this problem right here. Now, what are we going to do? Let's calculate the probability of A, B, intersection A and B, union A or B, for both of these cases. This case right here, porosity, permeability, samples, it's a bivariate distribution or sample set, 2 variables or features. And for this one right here. Now this will help us understand the addition rule and that idea of double counting. Now, hint here, this is literally just point counting. In other words, just count the number of samples in A, B over the total number of samples, okay? I'll show you the answers in 3, 2, 1. So this is what it looks like, pretty straightforward. Probability of A, just 6 samples in A. There's a total of 20 samples, and so we get 30% probability of A. Just frequentist counting and ratios. We assume we have enough samples. N is large enough, of course, again, and we keep it kind of simple here for demonstration. Now, probability of A and B, well, there's no intersection between them, so that's 0%, a null set of samples, 0% probability. And the probability of A union with B, the A or B operator, now we can see that we do the probability of A plus probability of B. There's no intersection, and it's just 60%. We can count the points in both, confirm that works. Same thing with this figure right here, but we have an intersection. 10% of the samples are in both A and B, and we can quickly observe the union operator here and see that if we do 40% plus 30%, we would get 70% without doing the subtraction, and very quickly you can confirm to yourself you've actually created a bias, you double counting. Subtract the 10%, you get 60%, and you can quickly see that this makes sense, that we do have a total of 12 data here. That is 60%. it works out if we do the proper addition rule with the subtracting to remove the double counting. Okay, so that's cool. Addition rule example to demonstrate it. Now, this is where things get real. We're getting into conditional probabilities now, and I think this is the real power. I think there's so many great things we can just do with conditional probabilities. Okay, so what is a conditional probability? What's the probability of event B occurring given A occurred? Now, the notation we'll use is the probability of B. This horizontal line, we'll read that as given, and that's event A. Okay, probability of B given A. How do we calculate that? The equation is going to be as follows. The probability B given A is equal to the intersection probability of A and B divided by the probability of A. Now let's go to the Venn diagram and see what that means. We have made the statement that A has occurred. Okay, so we no longer deal with omega. In a conditional probability, we have to conceptually shrink the space of possible outcomes to only A. Because we said A occurred, now our universe is only A. We can't see anything else. And so the Venn diagram was here with omega. Now this is our new Venn diagram. It's only A can occur. And so if you look at that, what's the probability of B given A occurred? It's the ratio of the intersection A and B divided by A. It makes perfect sense if we shrink our universe. So every time you hear a conditional probability, think of shrinking your universe. Kind of fun, eh? All right, so now let's generalize, because we've introduced the idea of conditional probability and we've defined it by this equation right here. Probability of B given A is equal to probability of A and B divided by the probability of A. Let's put some words around these terms. This is a conditional probability. We just stated that. This right here, and we could say it as probability of A and B, or just intersection A, B, is a joint probability. It's a joint probability because it considers more than one event at the same time, and this, in the denominator, is a marginal probability because it's only considering one thing at a time, one event at a time. Now, how do we visualize and think about this? How do we kind of put this all together? I would draw a plot like this. Now, if you look at it, we have a distribution of porosity. And if you're only concerned one feature at a time or one event at a time, this is going to be a marginal distribution, just porosity measures. This right here is a distribution of permeability. It's also a marginal distribution. And if we took all the points and we plotted and modeled them between porosity and permeability, that's a scatter plot. And we could fit some type of model to it, some kernel density, smoothing estimator of density. And don't worry, we'll get more into this. We'll talk about distributions in the next lectures. It would have some type of shape, that point cloud, and we can model that as a distribution in 2D. And we're considering two variables or features at a time. And so that would be a joint distribution. Now what we could do moving forward from that is we could calculate from those distributions probabilities. So I could pick an interval of porosity between here, and from that distribution I could calculate the number of outcomes that have that criteria, porosity in that range, and that's a marginal probability. If I pick an interval on permeability and I calculate the probability of being between those values, that would also be a marginal probability. Now, if I took both of those, a constraint or bin in porosity, a constraint and bin in permeability, that would create a square right here of criteria, porosity interval, permeability interval, and I could calculate a joint probability from the joint distribution. Okay, so far so good. This is really kind of cool stuff. So we could now have joint probabilities from combining these two criteria. Each of them individually would describe a marginal probability. Now, if I was to define a condition given porosity from here to here, I could go to this point cloud and I could look at all the permeability values that meet that criteria, and I could build a distribution right there. That would be a conditional distribution. And if I was to say, okay, give me a value or probability of being from here to here, That could be a conditional probability. I've shrunk my universe to that porosity constraint, and now I get a conditional probability of permeability given that porosity constraint. Okay, don't worry, we're going to reinforce this with some really nice practical examples. Let me just define some of the terms again that we just talked about. Marginal probability, probability of an event, irrespective of any other event. You don't consider any other event. Conditional probability, probability of an event given another event is already true. It already occurred. You shrunk your universe, and we use the notation X given Y, and so forth. Okay, and joint probability, probability of multiple events occurring together. Now we can use the notation X and Y, or X intersection Y. Later on, I'm going to get a little bit lazy and just break it down to just X comma Y to keep the notation really simple and compact. Now, given what we just learned about joints and conditionals and marginals, we can kind of expand our concepts of conditional probability. We can talk about a general form or recursion of conditional probabilities. And this is really, really interesting. So let's walk this through one step at a time. The statement is that the probability of C given B and A, so you see we got a conditional, and then we also have a joint here in the condition. That's super cool, is equal to the probability joint A intersection B intersection C divided by probability of A intersection B. Now let's go to the Venn diagram and prove that to ourselves. Okay, we said the probability of C given B and A. Okay, so let's take B and A. That's this area right here. So we shrink our universe to that. And now we need to calculate the probability of C given that. So that's going to be this area right here, which is the intersection A, B, and C, divided by A and B, this entire area right here. So I hope you can see by the Venn diagram that that holds up. Now let's do a substitution. Recall the definition of conditional probability. The probability B given A is equal to the intersection probability A and B divided by the probability of A. So what we can do with that now is we can reorder this. We can turn it into the probability of A and B is equal to the probability of B given A times the probability of A. We'll just take this denominator out and put it on the left-hand side. We can now substitute for the denominator in this first equation, and we get this form right here. You see that? Now this is super cool because if we take this form and simply take the denominator out again, put it on the left-hand side, we now get the joint probability of A and B and C is equal to the probability C given B and A times the probability B given A times the probability of A. Now, do you see that pattern? It's a super cool pattern. It's a recursion of conditionals. The joint right here can be solved for as the probability of C given B and A. Now we can take that apart as probability of B given A, and now we just take the probability of A. Okay, that pattern, if you look at it, can be expanded like this to any number of possible events. Now, why do we care about this? Well, when we get into many different machine learning methodologies, such as naive Bayes, we're going to find we use this to solve for a joint probability that would be very difficult to solve for otherwise. We can use this recursion of conditionals to make it a much more practical problem. Okay, so we went a little deep right there. We got into something a little bit more complicated. If you understand this, you're going to be getting pretty powerful on these conditional probabilities. Okay, so let's make sure that we understand what we're doing. We'll finish up with a little closure in conditional probabilities, and then we'll do an example. Okay, so closure with conditional probabilities. It turns out we have the same closure rules, but in this case, we've shrunk our universe, so it's a little bit different. So the probability of A given B plus the probability of not A given B is also going to be equal to 1. Now you see how this closure is working. We shrunk our universe to B as occurred. So take the Venn diagram, B as occurred, we shrink our universe there. Now you can see very quickly that the probability of A given B, this intersection, plus the probability of not A given B, this part right here, is equal to 1 because we shrunk our universe to B. Only B can occur now, so they have closure now. And of course, it works with A or B or any one of the events we're dealing with. Okay, so given all that we've learned about conditional probabilities, let's go ahead and solve some of these. Now you'll notice I made it a little bit tricky. You don't need to actually measure the areas. You can actually communicate all of this using the concepts of probability of A, B, and so forth, intersections. So go ahead and solve for each one of these conditional probabilities. Okay, I'll show you the answers in 3, 2, 1, and here they are. Okay, so what happened? So this is interesting. This first part is trivial. Case 1 is trivial because remember the numerator of a conditional probability by definition will have the joint, the intersection between A and B. And in this case, they're mutually exclusive. That's equal to 0, null set. And so all of the probabilities are just 0 here. Now in the second case, we have something really interesting going on here. We can take the probability, the definition of probability, the intersection of A and B divided by probability B. And what we're going to find out is that if we shrink our universe to B, A always occurs. And so in this case, it's just equal to 1. They're both equal to each other. This intersection of A and B is equal to probability of B. Okay. Now in the other case, we shrink our universe to A, and what's really cool is the probability of B given A just becomes the ratio of probability of B divided by probability of A. Now I hope these examples really helped you solidify the concept of conditional probability. Now I provide one more example here. This is just more point counting. Hint, hint, not a big deal. And we have event A is porosity, that's good, it's above 15%. Permeability, good, above 200 millidarcies will be our event B. And let's go ahead and solve for it by point counting, assuming we have a large enough experiment, you remember that. Probability of A given B, probability of B given A. Now I'm going to ask you a bonus question. And that is, how much information does B tell you about A and vice versa? Are they informative of each other? Do they share information? Knowing porosity, does it help you know permeability? Okay, so go ahead, work that out. See if you can get the bonus question too. It's pretty cool. And I'll show you the answer in 3, 2, 1. And here it is. Okay, simple. We can just color code and draw our boxes here, event A, event B, and both of them occurring together. And we can easily solve for the probability of A given B, the intersection, 8 points out of 20, just B alone, 11 points out of 20, and so we get 8 divided by 11, and so forth. Now, how much information does B tell you about A and vice versa? The way to think about it is this. The probability of A, just alone, the marginal, would be all of the points in A divided by total number of points, and that's 10 divided by 20, 50%. The probability of A given B is different. And we already solved for it up here as 8 divided by 11. So the probability of A alone was 50%. Probability of A given we already knew that we had good permeability is 73%. They are different, significantly different. Now we'll get into statistical testing significance, but let's just say those are quite different. So if I know that the permeability is good, it does tell me a lot about the porosity. My probability of good porosity jumped up from 50 to 73%, and we can do it vice versa. So what's it tells us? It tells us that we can't work with A and B independently. They're sharing information. Now we'll get more rigorous defining independence here shortly. Now here's a nice little example right here where we'll talk more formally about the idea of calculating joint, marginal, and conditional probabilities, and we'll do it from a table of frequencies. What have we done? We got a feature 1, fraction of shale, and we binned it up. We got feature 2, porosity, and we binned it up. And you could imagine we could take all of our point cloud and just count the number of data points inside of each one of these bins. We're just binning up a scatter plot and counting the frequencies in each bin so that we can easily start to make some calculations. Okay, so the joint distribution is really discretized here as a bunch of frequencies. Now, we could turn those frequencies or those joint counts into probabilities just simply by dividing by the number of total samples. In other words, the number of samples in this combination right here, this joint count, is 1. The total number of samples we have here, I think, is about 20%. And so we would expect that this probability joint right here would be 4%. We can go through the entire data set and do that. We'll do that on the next slide. The marginal distribution, how do we get the marginal distribution? It's the process of marginalization. In other words, what we're going to do is if we want the marginal distribution of x, we're going to integrate from negative infinity to positive infinity over the joint distribution over the feature we want to remove. In other words, it's a integration, or if we bend up the joint, it's a summation. So if I want the marginal fraction of shale 10%, I'm just going to sum over the column. I'm integrating over porosity to remove it. Isn't that cool? And if I want the marginal of porosity 15% per se, I would simply sum over the row, and that would get, and then all I have to do is divide by the total number of samples. That's marginalization. I've removed the influence of the fraction of shale by integrating it over it. Okay, so conditional distributions. You remember all that talk about shrinking our universe? We're still shrinking our universe. So we can solve for the conditional simply by looking at the joint and dividing by the marginalized. Okay, so what does that look like? If I want the conditional of porosity 20% given V shale of 10%, all I have to do is take this joint and divide it by the total number of samples in this column, where we have, in fact, we're conditional. We shrunk our universe to only V shale 10%. The fraction of shale can only be 10%. This is our universe now. We take that joint, divide by that new subset of just the column, and we get the conditional. Okay, so let's go ahead. Let's start with the joint probabilities. Really simple. So we can go all the way through our data set and simply take, we had one sample here divided by 25 total samples, that's 4%, 2 samples here, 3 samples here, not a big deal. So that's how we got the joint probabilities. Now to calculate the marginal probabilities, all we're going to do is sum over the columns to marginalize to get the marginal for just fraction of shale, sum over all of the rows to get the marginal for porosity. And for the conditional probability, we shrink our universe. We're basically standardizing by the count, the marginal within each one of the rows or the columns. Okay, so let's go ahead and work that out. I'm going to ask you to go ahead and do marginalization for both V shale, or fraction of shale, and for porosity, and to then calculate the conditional probability given porosity is equal to 15% for V shale given porosity is equal to 15%. I'll show you the answers in 3, 2, 1 right now. Okay, so what do we got here? Really, really simple. To get the marginal probabilities, we're going to integrate over the feature we want to remove. So we got V shale right here. And so if we want to know the marginal, V shale given 10%, we're just summing 4% plus 8%, 12% plus 4%, 16%. There it is. Boom, you get 24%. Just keep going. That's all we're doing. For the marginal of porosity, we just sum across the rows. And you can confirm very quickly, 25% case, that's 8%. The 5% case, that's 12% down here. Not a big deal. The conditional probabilities from this joint probability table, very straightforward. We just go ahead and shrink our universe. We said given porosity equal 15%, porosity equals 15% is right here. This part of the table is the whole world now. So the conditional of V shale equal 10% is simply going to be the case of 4% divided by, and that's 24%, that's going to be equal to 1/6. 8% divided by 24%, 1/3, and so forth. We shrunk our universe. Every time you hear a conditional probability, think about shrinking your universe. All right. Now, there might be some of you out there who want a little bit more hands-on opportunity. I put on GitHub at this address in my GitHub repository on Excel numerical demos, an example in Excel where I gave myself a frequency, joint frequency data set with a bunch of samples. You can edit that at will. It calculates the marginal frequencies and then converts them all to joint probabilities, marginal probabilities, and then it calculates one of the conditional sets of probabilities, conditional of V shale given a porosity equal to a specific value, I think 4.5%. Go ahead, you can play with that and get some understanding about joint, conditional, and marginal probabilities and distributions. Probabilities are these individual measures, the distributions when you take all of them together. So let's go ahead now and shift gears a bit. We're going to talk about the multiplication rule. Now what's really cool here is that this is going to lead us directly to Bayesian probabilities. So we're almost there. We're getting there. All right, the multiplication rule. This should not be a surprise at all. In fact, if you look really carefully, it is the reordering of the definition of conditional probability. If I took this probability of A and put it in the denominator on the left-hand side, that is the definition of conditional probability. So no surprises. We simply pulled the denominator out, put it on the other side, and so the multiplication rule is the joint probability of A and B intersection is equal to the conditional probability B given A times the marginal probability of A. Okay, now if events A and B are independent of each other, what that means is that this given A should have no influence on the probability of B. Knowing something about A should not impact the probability of B if they're independent, so the probability of B given A is just equal to the probability of B. We can substitute this part right here, and so given independence, we can say probability of A and B is equal to probability of B times the probability of A, under the assumption of independence. Okay, the general form of independence, of mutual independence between all of our events, is we can say the intersection of all of our AIs, I1 through K different events, is just going to be the product sum of all the probabilities. We're just going to multiply them together. So an example in the case of 3, K is equal to 3, is the probability of the intersection or joint A1 through 3 is simply the product sum or multiplication of all of the probabilities. Okay, this is pretty cool stuff. So if we assume independence, we can solve a lot of problems in a very simple manner. Let me give you an example right here. Event A is oil. Event B is porosity greater than 10%. We have the probability of oil 30%. Probability of good porosity is 50%. What's the probability intersection of A and B? And here's another one where we expanded to 3 possible events. All right, I'll show you the solutions in 3 seconds. 3, 2, 1. All right, very, very simple here. So if we go ahead and assume independent events, we can just multiply the probabilities by each other, and the result is we get probability of A and B is probability of A, B times probability of A, 30% times 50%, 15%. And with the 3 events too, we just keep multiplying them by each other to calculate the probability. Now, given that we said that if events are independent, we can find them just by the product sum, we can use that as a definition of independence or even a check for independence. So if we assume independence, we expect the probability of A and B to be the probability of B times probability of A. We expect the conditional probability of A given B to just be equal to probability of A, and the probability of B given A to just the probability of B. And we have the expanded general form in the case of the intersection of AI through K as just being the product sum of all the probabilities, the marginals. Okay, so we can use this as a definition of independence, and we can use it to check for independence. Now, I would not say we're proving independence. I would say that we can show that there is not likely independence if we violate that relation, but I would not suggest that we're completely proving independence. Okay, so let's just put it that way. It's a little bit of a soft check. So let's go ahead and give ourselves an example. We got well 1 through well 10. We're going to have a top, middle, and bottom unit, and for each one of them, we can only have one facies. Facies 1, 2, or 3. Event A1 is facies 1 in the middle. Event A2 is facies 3 in the bottom. Now, using these definitions, you could use any one of them, go ahead and try to disprove that we have independence here. Okay, so I'll give 3 seconds and then you go ahead, we'll look at the answer together. Okay, 3, 2, 1, here's the solution. A simple way to do this is to I always like drawing circles, boxing things off, making it clear what event A1 and A2 are. So A1 was middle is facies 1, so those are all of the A1s. The circles down here are the A2s, facies 3 in the bottom of the bottom unit or base unit. So we can calculate the probability of A1, probability of A2, and we can calculate the intersection A1, A2. We had 2 times that they both occurred out of 10. And so we have 50%, 60%, 20%. We can do a check. Probability of A1 times probability of A2 is equal to 30%. This is not equal to the intersection between the two. And so we can say that we don't feel this is independent. Now, once again, very difficult to prove independence, but it's pretty easy to show that it doesn't meet the criteria for independence, so therefore we suspect it's not independent. Now, this is very useful because imagine out in the field, if you had a data set, knowing that there's a degree of dependency between the middle and the bottom is a predictive model. It helps you make choices. In some cases, you may only know the facies in the middle and not know the facies in the base. Maybe you didn't collect core down there. You can use middle to make a prediction of the bottom because there's some information being shared between them. All right, we're going to stop there for right now. We've covered a lot of probability concepts around frequentist probability. In the next lecture, we're going to go ahead and get into Bayesian probability. And that's going to be a lot of fun. I really love that stuff. But I hope this was useful to you. Once again, I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. I share all my lectures online. I share content almost daily on Twitter. I'm the Geostats guy on Twitter. On GitHub, I have a repository with all of my worked out examples. That is Geostats Guy repository on GitHub. And I, of course, have this YouTube channel, which is Geostats Guy Lectures. All right. I hope this content is useful to you. Everybody, take care.